Module 23, Lecture A, Density Clustering. By the end of this lecture, you will be able to apply DBSCAN, HDBSCAN, and optics to discover density-based clusters, tune EPS, min samples, minimum cluster size, and distance metrics, and use BIRCH and clustering metrics for larger or structured clustering tasks. DBSCAN family. DBSCAN basics. DBSCAN finds clusters by looking for areas where data points are densely packed, rather than assuming a specific shape or center. This makes it useful for irregular patterns, such as curved or nested clusters, and for separating isolated points as noise. Its main idea is that a cluster is defined by local density, not by a prototype or central point. DBSCAN labels points as core, border, or noise based on how dense their surroundings are. Core points form clusters, border points attach to nearby cores, and noise points remain outside any dense region. This lets DBSCAN find clusters without forcing every point into one, making it useful for spotting outliers in areas such as fraud detection and environmental monitoring. DBSCAN finds clusters by looking for dense regions of data points. It grows a cluster from a dense core point by adding nearby points that are connected through other dense areas, then repeats this process for unvisited points. Points that are not dense enough or reachable from a core point are treated as noise, though they may later be included if they become reachable. Its main benefit is that the number of clusters does not need to be set in advance, but its parameters must be chosen carefully. Python code. DBSCAN basics. This demonstration uses simple synthetic data to show how DBSCAN identifies dense clusters and separates out noise points. The resulting labels are compared in a single scatterplot, making it easy to see which points belong to groups and which are treated as outliers. We import the main tools needed for a DBSCAN clustering example: NumPy for numerical work, Matplotlib for scatterplot visualizations, and Scikit-Learn for machine learning utilities. From Scikit-Learn, we use DBSCAN to find dense clusters and detect outliers, the MakeMoons dataset to create two interleaving half-circle clusters, and the StandardScaler to put features on comparable scales for better clustering performance. We generate synthetic data with Scikit-Learn's MakeMoons function, which creates two interleaving half-circles that are difficult for centroid-based clustering. The dataset contains 300 noisy samples to make it more realistic, and a fixed random state makes the results reproducible. The generated points and their true labels are then used to evaluate clustering performance. We add a few isolated two-dimensional points to the dataset to represent noise or outliers. These points are combined with the original data using a vertical stacking operation, expanding the dataset. This prepares the data for clustering methods that must detect and handle noisy points. We standardize the data with Scikit-Learn's StandardScaler, so each feature has a mean of 0 and a standard deviation of 1. This puts all features on the same scale, helping DBSCAN use its neighborhood size parameter consistently. Standardization is important because DBSCAN is sensitive to differences in feature scale. DBSCAN is used to find dense groups in scaled data and mark outliers. Here, it uses a neighborhood radius of 0.25 and requires at least 5 nearby points to form a dense region. After applying it to the data, each point receives a cluster label, while outliers are labeled as -1. To summarize DBSCAN results, first find the unique labels assigned to the data points, including the noise label. The number of clusters is the count of unique labels excluding the noise label, usually -1. The number of noise points is found by counting how many points received that -1 label. The output reports the Scikit-Learn version to support compatibility and reproducibility, then summarizes the DBSCAN results. It shows how many clusters were found and how many data points were labeled as noise, meaning they did not fit into any cluster. The plot is set up with a figure and axis. Then each unique DBSCAN label is processed in turn. Points with the current label are selected and drawn on the plot. Noise points, marked by DBSCAN with label -1, are shown as black crosses, while all other points are displayed as their assigned clusters. This makes the clusters and noise easy to distinguish visually. The plot is finalized by adding a title that emphasizes how DBSCAN finds dense, curved clusters and noise. The axes are labeled as Feature 1 and Feature 2. A legend identifies the clusters and noise points, and the plot is displayed so the clustering results can be visually analyzed. This script shows how DBSCAN clusters synthetic two-moon data, a shape that is difficult for centroid-based methods. After adding a few noise points and standardizing the data, DBSCAN finds dense, nonlinear clusters and labels oscillated points as outliers. The output reports the Scikit-Learn version, the number of clusters, and the number of noise points, while a scatter plot highlights the clusters and outliers. Epsilon and min samples. In DBSCAN, epsilon and minimum samples define what counts as a dense region. Epsilon sets how far to look around each point, and minimum samples sets how many nearby points are needed for a core point. Clusters grow by connecting these dense areas, while nearby points may become border points and isolated points are treated as noise. Unlike k-means, DBSCAN does not require choosing the number of clusters in advance and can find irregularly shaped groups. In DBSCAN, epsilon sets the distance for deciding when two observations are neighbors, so it strongly affects how clusters are found. If it is too small, real clusters may split apart or be labeled as noise. If it is too large, separate clusters may be merged. Choosing epsilon well depends on the data context and helps preserve meaningful groups without losing important detail. In DBSCAN, the minimum sample setting works with epsilon to decide whether an area is dense enough to become a cluster. Lower values allow smaller clusters to form, but can mistake noise for real structure, while higher values reduce noise but may miss small groups. These two settings should be tuned together based on the data scale and the goal of the analysis. Python code, epsilon, and min samples. Epsilon is a small positive value used in numerical methods. It helps define a precision threshold. Min samples is the minimum number of data points needed to form a valid cluster or region. Now let's look at a quick example. Epsilon equals 0.5. Min samples equals 5. This example adjusts DBSCAN's neighborhood settings to control how clusters are found. Epsilon and minimum samples define the required local density, which determines which points form clusters and which are treated as noise. We import the main tools needed for a clustering example: NumPy for numerical work, Matplotlib for plotting, and Scikit-Learn for machine learning. From Scikit-Learn, we use the DBSCAN clustering algorithm, the Make Moons dataset generator for testing on moon shake data, and StandardScaler to standardize the data before clustering. We create a curved two-moons dataset to test density-based clustering. It contains 300 samples with a small amount of noise to make clustering more realistic, and a fixed random seed ensures the same data is generated each time. We standardize the dataset features using Scikit-Learn's StandardScaler, so each feature has a mean of 0 and a standard deviation of 1. This makes distances between data points more comparable, which is important for clustering. The scaler is fitted to the data and applied in one step, producing scaled features ready for analysis. Before clustering, the code verifies that the scaled data has 300 samples and 2 features. If the data has a different shape, it raises an error to stop the process. This check helps ensure the clustering algorithm receives data in the required format. We create a DBSCAN clustering model with epsilon set to 0.25 and a minimum of 5 samples. These settings control how close points must be to form a dense region. The model is then applied to the scaled features, assigning each point to a cluster or marking it as noise. To summarize DBSCAN results, first collect and sort the unique labels, including the noise label, usually -1. The number of clusters is the count of unique labels that are not noise. The number of noise points is the count of data points assigned the noise label, meaning they were not placed in any cluster. The code reports key information about a DBSCAN clustering run. It shows the Scikit-Learn version for reproducibility, lists the main DBSCAN settings, such as epsilon and the minimum samples needed for a dense region, and summarizes the results by giving the number of clusters found and the number of points labeled as noise. To separate noise from clusters, create an array that marks noise points as -1 while keeping cluster labels unchanged. This makes the two types of points easier to distinguish in a plot. Then, set up a Matplotlib figure with a clear viewing size to show the data distribution. The scatter plot shows the first two scaled features on the horizontal and vertical axes. Point colors come from a color array that separates noise from clusters, using the Viridis color map to make the groups easier to distinguish. The points are sized for clear visibility. The plot is labeled to show the DBSCAN settings, with epsilon set to 0.25 and minimum samples set to 5. The axes are named for the two scaled features, and the plot is then displayed so the clustering results can be visually assessed. This script uses DBSCAN to cluster a noisy 2moons dataset. After generating and scaling the data, it applies density-based clustering with a small neighborhood size and a minimum of 5 nearby points. It reports how many clusters were found, excluding noise, and how many points were labeled as noise. A plot then shows how DBSCAN separates the dense moon-shaped groups and highlights outliers. Distance metrics. In DBSCAN, the distance metric determines which points count as neighbors, so it strongly shapes the clusters found. Euclidean distance works well for continuous, similarly scaled data, but features with very different scales can distort results unless they are standardized. Choosing the metric carefully is essential because it affects how density is measured, whether clusters are separated or merged, and which points are treated as noise. Distance metrics define what similarity means for a dataset, so the choice should match both the data structure and the clustering goal. Manhattan distance fits grid-like movement. Cosine distance works well for high-dimensional data, where direction matters more than size. And binary or categorical data may need specialized measures. The key is to choose a metric that reflects the kind of similarity you want to capture. Distance metrics strongly shape how DBSCAN-based methods such as HDBSCAN and optics find clusters, because they depend on which points are considered close neighbors. HDBSCAN builds a hierarchy of density-connected regions, while optics reveals cluster structure across different scales, but both can be misled by a poor metric. This is especially important in high-dimensional data, where distances may become less meaningful. Careful preprocessing and metric selection help make these algorithms reflect the real similarities in the data. Python code, distance metrics. DBSCAN neighborhoods depend on the distance metric used, and scaling can change which points are considered close. As a result, different metrics or scaling choices can produce different cluster labels. We begin by importing the main tools needed for clustering work. NumPy supports efficient numerical operations. Matplotlib helps visualize the results, and Scikit-Learn provides machine learning utilities. From Scikit-Learn, we use DBSCAN for density-based clustering, a blob data generator for creating test data, and a StandardScaler to normalize features before analysis. Synthetic data is created with Scikit-Learn's makeBlobs function to form two compact clusters centered at -2, 0, and 2, 0. A fixed random state makes the generated points reproducible each time the code runs. The function also provides the true group labels, giving a controlled dataset for testing clustering algorithms. We create a copy of the original points so the data stays unchanged, then stretch the second feature by multiplying it by 8. This makes differences in that dimension dominate the raw Euclidean distance, causing it to become misleading. The distorted data helps show why scaling is needed to make distance comparisons more reliable. We use Scikit-Learn's StandardScaler to put each feature on the same scale, giving it a mean of 0 and a standard deviation of 1. This prevents one stretched feature from dominating distance calculations, helping DBSCAN form clusters based on the data's true structure. DBSCAN is applied to both the stretched and standardized data to compare clustering results. For the stretched data, a larger neighborhood radius of 1.2 is used, while the standardized data uses a smaller radius of 0.45 because the values have been scaled. In both cases, clusters require at least 5 points and use Euclidean distance. The key idea is that pre-processing can significantly change the cluster labels produced by the same algorithm. To compare DBSCAN results, we count the unique cluster labels in both the raw and scaled data, excluding the noise label, -1. We also count how many points are labeled as noise in each case. These two measures show how scaling changes the number of detected clusters and the amount of noise. We first report the Scikit-Learn version to support reproducibility. Then, we compare DBSCAN results on the raw stretched data and the scaled data by showing the number of clusters and noise points found. This highlights how standardization can change the clustering outcome by making Euclidean distances more meaningful. We create a Matplotlib plot and use a scatter plot to show the scaled data points. The first two columns provide the horizontal and vertical positions, while the cluster labels determine each point's color using the tab 10 color map. This makes the clusters easy to compare and helps show how scaling affects their structure. The plot is labeled to show that scaling makes Euclidean distance useful for DBSCAN clustering. The axes represent the first and second scaled features, and a legend identifies the cluster labels. The visualization is then displayed using Matplotlib's show function. This script shows why feature scaling matters when using DBSCAN for clustering. It creates two compact point groups, stretches one feature so distance becomes misleading, then compares clustering before and after standardization. The unscaled data produces different clusters and noise points, while the scaled data better reflects the intended density structure. The results are printed, and the scaled clustering is visualized to show the clearer separation. Advanced Density Tuning, HDBSCAN Tuning. HDBSCAN finds clusters in data where groups can have different densities, such as tightly packed or more spread out customer segments. Rather than relying on one fixed distance cutoff, it builds a hierarchy of density-connected regions and selects the most stable clusters. Good tuning helps reveal meaningful dense structures and separate them from noise, while poor tuning can split natural groups or merge distinct ones. When tuning HDBSCAN, the key settings are minimum cluster size, minimum samples, and the distance metric. Minimum cluster size controls the smallest group the algorithm will treat as a cluster, while minimum samples controls how strict the algorithm is about density. Higher minimum samples usually creates fewer clusters and more noise, while lower values can find more clusters but may be less stable. Together, these settings help balance meaningful cluster size with reliable density requirements. In HDBSCAN, The distance metric shapes how the algorithm understands density. So it should match the data type, such as spatial distance for geographic data or cosine similarity for text embeddings. For mixed features, preprocessing helps prevent variables with larger ranges from dominating the results. Good tuning balances stable clusters, reasonable noise, and real-world meaning, aiming for clear patterns while accepting that some points may not belong to any cluster. Python code HDBSCAN tuning. This example shows how HDBSCAN can be tuned on synthetic clusters with different densities. Adjusting the minimum cluster size affects how many points are treated as noise and how many clusters are found. The result illustrates one tuned clustering outcome. This setup imports the main tools needed for a clustering workflow. NumPy handles numerical arrays, Matplotlib creates visualizations, and the Scikit-Learn version helps with reproducibility. The workflow also brings in HDBSCAN for clustering, synthetic data generation for testing, the silhouette score to evaluate cluster quality, and standard scaling, so features contribute more evenly to distance-based clustering. We generate synthetic two-dimensional data with the makeBlobs function from Scikit-Learn to create 3 clusters. The clusters have different sample sizes, centers, and spreads, producing groups with varied densities and locations. A fixed random state makes the results reproducible, and the dataset is useful for testing clustering methods such as HDBSCAN. A fixed random seed is used so the results can be reproduced. 35 two-feature noise points are generated uniformly between -5 and 5, then combined with the existing cluster points into one dataset. This creates a noisy clustering dataset for testing how robust algorithms like HDBSCAN are. The features are scaled with Scikit-Learn's StandardScaler, so each one has a mean of 0 and a standard deviation of 1, making clustering distance comparisons more balanced. After scaling, the array shape is checked to confirm it contains 315 data points and 2 features. If it does not, an error is raised to signal a mismatch in the data. The setup tests several minimum cluster sizes to see how they affect clustering performance. For each run, it records key results such as the number of clusters, the share of noise points, and the silhouette score. This makes it possible to compare settings systematically and choose the one that produces the clearest clusters. The process tests several minimum cluster sizes for an HDBSCAN model using scaled features, a fixed minimum samples value of 10, and Euclidean distance. For each setting, it records how many clusters are found, how much data is labeled as noise, and, when more than one cluster exists, the silhouette score to assess cluster separation. These results are stored as summary rows for comparing the different settings. An HDBSCAN clustering model is created with a minimum cluster size of 25 and minimum samples set to 10, which helps control cluster formation and how noise is identified. It uses Euclidean distance to compare points, then fits the model to the scaled feature data. After fitting, each point receives a cluster label, or is marked as noise, and these labels can be used for later analysis or visualization. The code reports the Scikit-Learn version for reproducibility, then prints a neatly formatted summary of clustering results. For each result, it shows the minimum cluster size, number of clusters, noise percentage, and silhouette score. If the silhouette score is invalid, it displays it as not available. Otherwise, it rounds the score to 2 decimal places for easier comparison. We create a scatter plot to visualize the HDBSCAN clustering results, using the first 2 scaled feature columns as the horizontal and vertical coordinates. Each point is colored by its assigned cluster label, with a distinct color map to separate groups visually. Styling such as moderate point size, black edges, and thin outlines makes the clusters easier to see, including points treated as noise. The plot is finalized by adding a title that notes HDBSCAN was tuned with a minimum cluster size of 25. The axes are labeled as Scaled Feature 1 and Scaled Feature 2, and a legend identifies the cluster labels. The completed plot is then displayed so the clustering results can be visually assessed. This script shows how to tune HDBSCAN on synthetic data with clusters of different densities and added noise. After scaling the features, it compares several minimum cluster size settings using the number of clusters found, the share of points marked as noise, and the silhouette score. It then visualizes one selected result, using colors to show the detected clusters and noise points. Minimum cluster size. In density-based clustering, the minimum cluster size controls when a group of points counts as a real cluster instead of noise. In methods like HDBSCAN, smaller values reveal finer, smaller groups, while larger values emphasize broader and more stable structures. The best choice depends on whether the analysis should capture small but meaningful segments or focus only on larger, more robust clusters. Choosing a minimum cluster size requires balancing statistical results with domain knowledge. If it is too small, clusters may become fragmented and meaningless. If it is too large, distinct or important smaller groups may be missed. A practical approach is to try several values and choose one that produces clusters that are stable, interpretable, and useful for decisions. Choose the minimum cluster size in density-based clustering, together with settings like density sensitivity and the distance metric. In HDBSCAN, it influences which clusters are extracted and which points are treated as noise. This choice is especially important in high-dimensional data, where distances can behave differently. Judge clusters by whether they are coherent, explainable, and useful for real-world insight, not by size alone. Python code. Minimum cluster size. This example shows how changing the minimum cluster size in HDBSCAN affects the groups it finds. Comparing two beginner settings illustrates how the method can reveal either broader or smaller clusters. The script imports key tools for clustering analysis: NumPy for numerical work, Matplotlib for visualization, and Scikit-Learn utilities for generating synthetic blob data, running HDBSCAN clustering, and evaluating results with the silhouette score. It also imports Scikit-Learn itself, so the script can check the library version later. We generate synthetic data with Scikit-Learn's makeBlobs function to create 3 clusters with different sizes and spreads. The clusters contain 35, 90, and 160 points, centered at -3, 0, 0, 2, and 3, 0. Their standard deviations increase from 0.25 to 0.65, making each cluster progressively more spread out. And a fixed random state ensures the results can be reproduced. A few scattered points are added to the dataset to act as possible noise for clustering. These points are combined with the existing data using NumPy's vertical stacking function, so the clustering algorithm can be tested on how it handles outliers, either marking them as noise or assigning them to clusters. The code verifies that the point dataset has 290 rows and 2 columns before clustering. If the dimensions are wrong, it raises an error, helping catch invalid data early and prevent later clustering problems. We compared 2 HDBSCAN models to see how minimum cluster size affects the results. One uses 15 points, and the other uses 70. Both use 5 minimum samples to help identify core points. Each model is fit to the same point dataset, and the fit and predict method returns a label for every point, showing its cluster assignment or marking it as noise with -1. This function counts the number of real clusters in a set of labels while ignoring noise. It first keeps only the unique labels, removes the noise label, usually -1, and then returns how many labels remain. That final count represents the detected clusters, excluding noise. The code compares two clustering models with different minimum cluster sizes. It counts noise points by finding labels marked as -1, reports the Scikit-Learn version for reproducibility, and prints the number of detected clusters and noise points for each model. This shows how changing the minimum cluster size affects the level of detail in the clusters and the amount of data treated as noise. To evaluate the clustering, we first exclude noise points by keeping only points whose labels indicate they belong to a cluster. We then compute the silhouette score on those clustered points to measure how well each point fits its own cluster compared with others. The rounded score gives a concise measure of clustering quality under the larger minimum cluster size setting. We create a Matplotlib plot and use a scatter plot to show the data points by their two coordinate columns. The points are colored by the cluster labels from the larger HDBSCAN model, with clear sizing and black outlines to make the groups easier to see. This helps illustrate how increasing the minimum cluster size changes the way the data is grouped. The plot is finalized by adding a title that notes HDBSCAN clustering with a larger minimum cluster size. The axes are labeled as Feature 1 and Feature 2, and a cluster legend is added to help distinguish the groups. The plot is then displayed so the clustering results can be viewed visually. This example shows how the minimum cluster size setting in HDBSCAN changes clustering results. Using synthetic data with clusters of different densities and added noise, a smaller minimum size finds more detailed clusters, but marks more points as noise, while a larger size produces fewer clusters with less noise. A silhouette score and visualization are used to assess the larger setting, highlighting the trade-off between cluster detail and sensitivity to noise. Optics parameter tuning. Optics is useful for finding clusters when density varies across a dataset, because it orders points to reveal density structure instead of relying on one fixed neighborhood radius like DBSCAN. Its key setting is the minimum samples parameter. Lower values can detect smaller, finer patterns, but may treat noise as clusters, while higher values are more stable, but can miss small groups. In customer data, this means lower settings may reveal niche communities, while higher settings emphasize broader market segments. In optics, EPS sets the maximum radius for checking nearby points, rather than acting as a strict clustering cutoff, as in DBSCAN. If it is too small, the algorithm may miss connections in wider or irregular clusters. If it is too large, it can slow computation and include weaker relationships. Choose EPS based on the scale of neighborhood patterns you want to study, such as city blocks versus broader neighborhoods in geographic data. In optics, the distance metric shapes how neighborhoods are defined, so it should match the data. Euclidean distance suits continuous, similarly scaled features. Manhattan distance can fit movement across separate dimensions, and cosine distance helps when direction matters more than size. Features should be scaled so one variable does not dominate, and the reachability plot should be checked to confirm meaningful dense regions and transitions. Python code, optics parameter tuning. This example shows how tuning optics affects clustering on synthetic data. Changing the parameters changes how dense neighborhoods are identified, and the resulting labels reflect one selected tuned setting. This setup imports the main tools needed for a clustering example. NumPy supports efficient numerical work, Matplotlib is used for plotting, and Scikit-Learn provides machine learning utilities. From Scikit-Learn, the optics clustering algorithm is used to find density-based clusters. The makeBlobs function creates synthetic clustered data, and the StandardScaler prepares features by giving them a mean of 0 and a standard deviation of 1. The synthetic dataset uses two cluster centers, one at -2.5 on the x-axis and one at +2.5, both with a y value of 0. The first cluster has a small standard deviation of 0.35, making it dense, while the second has a larger standard deviation of 1.0, making it more spread out. This creates clusters with different local densities for testing how well a clustering algorithm detects varying density patterns. The code uses Scikit-Learn's make-blobs function to create synthetic data with two clusters. The clusters contain 120 and 180 points, centered on opposite sides of the x-axis, with their spread controlled separately, so one can be more dispersed than the other. A fixed random state makes the generated data the same every time, which supports reproducible teaching examples. The code uses Scikit-Learn's StandardScaler to put each feature on the same scale, giving them a mean of 0 and a standard deviation of 1. This helps clustering treat both coordinates equally, so one feature does not dominate because of its larger scale. The fit and transform step calculates the scaling values and applies them to produce the scaled data. The code verifies that the dataset contains 300 rows and 2 features, confirming it is properly structured for clustering. If the dimensions are incorrect, it raises an error to signal that preprocessing may have failed before the analysis continues. We define several parameter settings to test the optics clustering algorithm. The configurations vary the minimum number of samples needed to form a cluster and the maximum epsilon value, while using Euclidean distance throughout. Comparing these settings helps show how parameter choices influence cluster formation and noise detection. The code first prints the Scikit-Learn version to help confirm compatibility and available features. It then prints a table header that organizes the optics clustering results, including the settings used, the number of clusters found, and how many points were labeled as noise. The process tests several optics clustering configurations by creating a model for each parameter set and fitting it to the scaled features. For each run, it assigns cluster labels, treats -1 as noise, and counts both the detected clusters and the noise points. It then reports the parameter settings together with these results, so the configurations can be compared. We configure an optics clustering model for clear visualization by requiring at least 20 samples per cluster and limiting the neighborhood radius to 1.5. It uses Euclidean distance and the C method, which helps detect clusters with different densities. The code uses the optics clustering algorithm on the scaled features. It runs the model's fit and predict method to assign each data point a cluster label, while points labeled -1 are treated as noise. This helps reveal the data's structure based on the chosen clustering settings. A plot is created with a 7 by 5 inch canvas. Then the data points are shown using a scatter plot. The first 2 scaled feature columns provide the horizontal and vertical positions. Each point is colored by its optics cluster label using the tab 10 color map, with a moderate point size so the clusters are easy to see. The plot is labeled to show the optics settings used, with a minimum of 20 samples and a maximum epsilon of 1.5. The axes identify the first and second scaled features, and a legend explains the cluster labels. The plot is then displayed to show the clustering results. This script shows how optics clustering responds to different parameter settings on synthetic data with 2 clusters of different densities. After scaling the data, it tests several configurations and reports how many clusters and noise points each one produces. It then visualizes one selected setting using 20 minimum samples and a maximum epsilon of 1.5, with colors showing the density-based groups found by optics. Large-scale clustering. Reachability plot insights. A reachability plot helps interpret the cluster structure found by optics, especially in large or uneven datasets. It orders points by density connection and shows each point's reachability distance, with low valleys marking dense clusters and high peaks suggesting boundaries or noise. This makes it useful for spotting clusters that have different densities. When reading a reachability plot, focus on the overall shape rather than exact values. Broad, deep valleys suggest large, stable clusters, while narrow valleys may indicate smaller, meaningful groups. Smaller dips inside a valley can reveal subclusters within a broader cluster. Overall, the plot shows how density changes across the data and helps you choose between broad, fine-grained, or mixed clustering solutions. Reachability plots give a compact view of density patterns in large clustering tasks, helping analysts choose parameters, extract clusters, and identify noise. They show whether the distance measure and neighborhood size are working well and whether clusters are truly separated. Used alongside scalable clustering methods and quantitative metrics, they connect algorithmic results with practical insight, such as spotting anomalies or outliers. Python code, reachability plot insights. This example shows how optics reachability distances reveal clustering structure. Valleys in the plot indicate dense clusters at different scales, helping identify the overall clustering pattern. We import the main tools needed for an optics clustering workflow: NumPy for numerical arrays, Matplotlib for plotting reachability distances, and Scikit-Learn components for clustering, data generation, and preprocessing. The optics algorithm identifies clusters with varying densities. Synthetic blob data provides a test dataset, and standard scaling ensures features contribute evenly to distance calculations. We also check the Scikit-Learn version to support compatibility and reproducibility. To study density, we create 3 synthetic clusters centered along the x-axis at -4, 0, and +4, all with the same y position. Each cluster is given a different spread: 0.25, 0.65, and 1.1. These spreads make the groups range from tightly packed to more dispersed, allowing comparison of different cluster densities. We generate synthetic clustered data using Scikit-Learn's makeBlobs function to test a clustering algorithm. The data includes 3 clusters with different sample sizes, centers, and spreads, so the clusters vary in both size and density. A fixed random state is used to make the results reproducible. To add realistic noise, a reproducible random generator is used to create 35 two-dimensional points spread uniformly between -6 and +6. These points are then added to the existing feature data, increasing variability and making the clustering task more challenging. We use Scikit-Learn's StandardScaler to put each feature on the same scale, giving it a mean of 0 and a standard deviation of 1. This makes distance comparisons fair across features, which is important for distance-based clustering methods, such as optics. The code verifies that the scaled data contains at least 50 observations before running optics clustering. If there are fewer, it stops with an error, helping ensure the clustering analysis has enough data to be meaningful. We configure an optics clustering model to find density-based clusters in the scaled data. It requires 12 nearby samples to form a cluster, uses a chi value of 0.05 to detect cluster boundaries, and sets the minimum cluster size to 8% of the dataset. Fitting the model computes reachability distances and orders points by density connectivity, helping reveal clusters with different densities. We use the optics model's learned ordering to get the reachability distances, which show the data's density structure. Infinite values are then removed, so the analysis focuses only on meaningful finite distances for interpreting the clustering results. We first copy the ordered reachability distances so the original data stays unchanged. Any infinite values, which can appear when points are not reachable under the chosen settings, are replaced with the largest finite reachability distance. This keeps the reachability plot on a consistent scale and makes the clustering structure easier to interpret. To summarize optics results, count the unique cluster labels after excluding the noise label, usually -1. This gives the number of clusters found. Then count how many points have the noise label to find the total number of noise points in the dataset. The code reports the Scikit-Learn version to support compatibility and reproducibility, then summarizes the optics clustering results. It shows how many clusters were found and how many data points were labeled as noise, helping indicate the main group structure and the amount of outlier data. This plot visualizes reachability distances from the optics ordering to help identify clustering structure. After setting up the figure, the reachability distances are drawn as a clear line plot, with labels for ordering position and reachability distance. The title highlights that valleys in the plot indicate dense clusters, and a light grid improves readability before displaying the result. This script uses the optics clustering algorithm to find groups in synthetic data with different densities and added noise. After standardizing the features, optics estimates reachability distances to separate dense clusters from noise. The results include the number of clusters found, the number of noise points, and a reachability plot where valleys show denser cluster regions. BIRCH clustering. BIRCH is a clustering method designed for large or complex datasets. Instead of comparing every data point directly, it scans the data and builds a compact clustering feature tree that summarizes nearby observations by their count, location, and spread. This reduces memory and computation needs, while still helping reveal broader cluster patterns in data such as transactions or sensor readings. BIRCH clusters data in two main stages. First, it builds a clustering feature tree by adding each point to a compact summary when possible, or creating a new summary when needed. A threshold controls how detailed these summaries are, with smaller values producing finer subclusters and larger values producing broader ones. Then the subclusters are treated as a smaller dataset and can be grouped further, such as into broader customer segments in a retail setting. BIRCH is useful for scalable, interpretable clustering when data forms compact groups, but it is less effective with irregular cluster shapes or varying densities, where methods like DBSCAN may work better. Because BIRCH depends on distance, features must be scaled, so one variable does not dominate the result. It is often used to compress large datasets before further clustering, making exploration and parameter tuning more efficient. Python code, BIRCH clustering. This demonstration applies BIRCH to compact synthetic clusters and compares different threshold settings using clustering metrics. The goal is to show that choosing an appropriate threshold can produce clearer, better separated clusters. This setup imports the main tools needed to test and evaluate BIRCH clustering. NumPy supports numerical array operations, Matplotlib helps visualize the results, and Scikit-Learn provides the clustering and pre-processing tools. The BIRCH algorithm is used for clustering large datasets, synthetic blob data is generated for testing, the silhouette score measures clustering quality, and standard scaling ensures all features are treated equally. We create a synthetic dataset with Scikit-Learn's makeBlobs function to test clustering algorithms in a controlled way. The dataset contains 900 points arranged into 4 clusters, with a standard deviation of 0.75 to control how spread out the points are. A random state of 42 makes the results reproducible each time the code runs. Before clustering, we scale the features with Scikit-Learn's StandardScaler, so they are comparable. This matters for distance-based methods like BIRCH, where features on larger scales could otherwise dominate the results. The scaler learns each feature's mean and standard deviation, then centers the data around 0 and scales it to unit variance, producing features ready for clustering. Before fitting the clustering model, the code verifies that the scaled feature data has 900 rows and 2 columns. If the dimensions are different, it raises an error to stop the process. This check helps ensure the data is in the expected format and prevents problems during model fitting. A BIRCH clustering model is created with a threshold of 0.45, which sets how close points must be to group together. The model is set to produce 4 final clusters, then fitted to the scaled feature data. Using the fit and predict method, it assigns each data point a cluster label based on the patterns found by BIRCH. To evaluate the BIRCH clustering results, we first count the distinct cluster labels to find how many unique clusters were identified. Then we compute the silhouette score using the scaled features and cluster labels to measure how well the clusters are separated. A higher score means the clusters are more clearly defined. We fit a second BIRCH model with a threshold of 0.2 to see how this setting changes the clustering. By leaving the number of clusters unspecified, the algorithm chooses clusters from the scaled data on its own. The resulting labels show each point's cluster assignment and help reveal whether a lower threshold produces finer subclusters. The output checks the Scikit-Learn version for reproducibility, then reports how many clusters the BIRCH model found. It also prints the silhouette score to indicate how well the clusters are separated. Finally, it shows how using a smaller threshold creates more subclusters, demonstrating how threshold granularity affects the clustering result. A scatter plot is created to show the final BIRCH cluster assignments in the scaled feature space. The first 2 scaled features are plotted on the horizontal and vertical axes, and each point is colored according to its cluster label using a distinct color map. The point size is adjusted to make the clusters easier to see. The plot is finalized by adding a clear title for BIRCH clustering after feature scaling, labeling the 2 scaled feature axes, and including a cluster legend based on the scatter plot. The plot is then displayed so the clustering results can be visually inspected. This example applies the BIRCH clustering algorithm to synthetic data with 4 groups. After scaling the features, it fits a model aimed at 4 clusters and evaluates the result with a silhouette score to measure separation quality. A second model uses a smaller threshold to reveal finer subclusters, showing how threshold choice affects granularity. The output reports the clusters found and visualizes them with a scatter plot for easier interpretation. Clustering performance metrics. Clustering performance metrics help judge whether discovered groups are meaningful, stable, and useful. Because clustering has no predefined labels, evaluation focuses on whether similar observations are grouped together and different ones were separated. These metrics are useful for comparing clustering approaches, but they should always be interpreted with domain knowledge and practical goals in mind. Internal clustering metrics evaluate clusters using only the data and assigned labels, which is useful when true labels are unavailable. They measure whether points within a cluster are close together and whether different clusters are well separated. However, these metrics can favor certain cluster shapes and may not fully reflect the value of density-based or hierarchical results. For methods like BIRCH or density-based clustering, it is important to judge whether the clusters represent meaningful patterns, not just whether they score well on traditional metrics. When reference labels or business goals are available, external evaluation helps compare them with clustering results. But clusters may also reveal useful patterns that existing categories miss. In areas such as medicine or cybersecurity, these new groupings can point to important treatment responses or unusual network behavior. For large datasets, evaluation should also consider memory and runtime, using efficient methods such as BIRCH when needed. A strong clustering assessment combines metrics, visual checks, stability testing, and domain knowledge to find results that are both meaningful and practical. Python code, clustering performance metrics. This section compares clustering metrics on compact synthetic data. BIRCH first summarizes the data, then assigns cluster labels. The results show that no single score fully captures clustering quality, so multiple metrics are needed for a more reliable evaluation. We import the main tools needed for a clustering workflow: NumPy for numerical arrays, Matplotlib for visualization, and Scikit-Learn for machine learning. From Scikit-Learn, we use the BIRCH clustering algorithm, a synthetic data generator for creating clustered test data, and 3 evaluation measures: the Calinski-Harabasz score, Davies-Bouldin score, and silhouette score. Together, these tools let us build, visualize, and assess clustering results based on how compact and well-separated the clusters are. A synthetic dataset is created with Scikit-Learn's makeBlobs function to produce 900 data points grouped into 4 natural clusters. Each cluster has its own spread, controlled by different standard deviation values, so the groups vary in shape and size. A fixed random state of 42 ensures the same dataset is generated every time for consistent testing and evaluation. Before clustering, the code verifies that the feature data has the expected size: 900 rows and 2 columns. If the dimensions do not match, it raises an error and stops the process. This early check helps ensure the data is correctly formatted and prevents problems later in the analysis. A BIRCH clustering model is created to group the data into 4 clusters. Its threshold controls how sensitive the clustering is, while the branching factor limits how many subclusters can appear in each tree node. After the model is fitted to the generated features, each data point receives a cluster label for later analysis. We first count how many distinct clusters the BIRCH model found by identifying the unique cluster labels. If the result is fewer than 2 clusters, an error is raised because clustering performance metrics are not meaningful with only 1 cluster. This check ensures the later evaluation is valid. To evaluate clustering quality, we use 3 common scores. The silhouette score and Calinski-Harabasz score are better when higher, showing clearer separation and stronger cluster structure. The Davies-Bouldin score is better when lower, indicating that clusters are more distinct from one another. The code reports key information about a BIRCH clustering run. It shows the Scikit-Learn version for reproducibility, the number of clusters found, and 3 evaluation scores. The silhouette and Calinski-Harabasz scores are better when higher, while the Davies-Bouldin score is better when lower, helping judge how well separated and well formed the clusters are. Create a 6 by 4 inch plotting area. Then make a scatter plot using the first feature on the horizontal axis and the second feature on the vertical axis. Color each point by its cluster label, using distinct colors and a visible point size. This makes it easier to compare the clustering scores with the actual structure of the data. The plot is labeled to show that it presents BIRCH clustering results evaluated with internal metrics. The axes are named Feature 1 and Feature 2 to identify the 2 data dimensions, and the visualization is then displayed so the clustering results can be viewed. This script tests BIRCH clustering on a synthetic dataset with 4 groups. It reports the Scikit-Learn version, the number of clusters found, and 3 internal quality scores: silhouette and Calinski-Harabasz, where higher is better, and Davies-Bouldin, where lower is better. It also checks that at least 2 clusters exist, so the metrics are meaningful, then plots the clustered points to compare the visual grouping with the numerical results. In this lecture, you learn to apply DBSCAN, HDBSCAN, and optics to discover density-based clusters, tune EPS, min samples, minimum cluster size, and distance metrics. And use BIRCH and clustering metrics for larger or structured clustering tasks. In the next lecture, Lecture B, we will go over biclustering validation.
Thank you for your attention. See you all in the next lecture.